Let's talk a little bit more about nuclear force, and let's try to go deeper into the problem of nuclear force. And if I have to remind the idea that what we have nucleons inside the nucleus, and the protons and neutrons inside the nucleus, they constitute the nucleons of the nucleus. Now, this nuclear force, it does not extend, it does not go beyond, it does not go to infinity, but it's confined to extremely small distance around the nucleons, around the source. So the precise nature of this nuclear force, it was not known earlier than 1935. And when this Japanese physicist Yukawa, he gave the new basic idea, and this idea paved the way of our present understanding of nucleus. Even though what we understand presently about the nucleus is extremely incomplete, but whatever we could understand to a very good degree of understanding, it was a result of the idea of Yukawa. And what he predicted, he basically predicted the existence of new particles. He predicted the existence of new particles, and these particles are elementary particles, and now they are called as pi mesons, pi mesons. And what he did is he hypothesized that the two nucleons they experience an attractive force. They experience this attractive force at very small distances because of what we call as exchange of these pi mesons, these virtual particles, pi mesons. Now, this exchange of these the exchange now this exchange of these particles, it takes place in very short times. This is a very important point. Very short time. I would like to put an order of that time. That's from 10 to the power of minus 23 to 10 to the power of minus 24 seconds, and is typically and is certainly typically, or I should say, typical nuclear force. Typical condition of a nuclear force. Now, since the exchange takes place in very, very short time, the uncertainty principle comes in action. Uncertainty principle. And what uncertainty principle requires that no visible change in the masses of nucleons will be observed, because the exchange of the particles is so fast, the time is so small that there will not be any visible change in masses of these protons and neutrons, whom we call as nucleons. So what happens is that what we have is this produces a rapid Meson exchange field between protons and neutrons, in which Meson is a quantum of nuclear force. For the time being, this Meson is quantum of nuclear force. And in the present situation, very qualitatively analogous. If we take the example of two boys grappling for control of a volleyball or a basketball, the one who grabs the ball from the other, and then the second snatching it back again. The continual exchange of this ball between the two boys is results in some kind of interaction, and this interaction can prove to be attractive in nature. And I had already given an example of a bone that the two dogs trying to take the custody of a bone. We have a dog, and in doing so, they are able to generate an attractive force. So this can be analyzed physically in a sense like this. What I believe is there is no physicality involved in quantum mechanics, but this is a very good example to have an idea about how this force comes in action when there is the rapid exchange of these particles between these nucleons. Now, what Yukawa assumed that the force between the two stationary nucleons, if we have two stationary, the condition is stationary nucleons. And what he did, he took it analogous to the electrostatic field between two stationary charged particles, as if we have two charged particles at rest, and then the correct fundamental relationship between the mass of the pion and the nature of the force between the two nucleons is established. So we have two nucleons where both of them are at rest, and there is a kind of a force between these nucleons. And if we talk about Maxwell's equations, they freely describe the propagation of electromagnetic waves in the absence of any source. And the same question, the same argument also describes the electrostatic field of a stationary point charge, and thereby the potential energy of interaction of two stationary point charges. So what am I trying to tell here is that the electrostatic potential due to one stationary charge, if I take the charge Q1 and charge Q2, the electrostatic potential that we have on one stationary charge satisfies the wave equation everywhere outside that charge. And this solution of the wave equation has some special properties. That is, it is spherically symmetric. So this point is exploited out here, spherically symmetric and static when it comes to the nucleons, when nucleons are assumed. Now let us imagine that we consider the wave equation satisfied by freely propagating Meson field. Okay. And try to go for the wave equation which is spherically symmetric and static in nature. This will certainly lead us to know the form of potential of the nuclear force field that we have if we take the same kind of situation out here in a single nucleon, and this single nucleon assumed to be at the origin at position 0, 0, 0. Now suppose this potential is represented by some V of R, and then the interaction energy of the two stationary nucleons that we have is separated by some R. And what will be that? This potential will be proportional. This separation will be proportional to this V of R. And we will have the constant of proportionality will describe the strength of coupling between these two nucleons. In the nucleon field, in the pion field that we are assuming here. Now, the wave equation that we have, which is satisfied by this pion field wave function is basically the Klein-Gordon equation. Okay, so we may also track it down like the wave equation satisfied by the Payen-de Broglie wave function, which is basically a Klein-Gordon equation. And let the mass of this Payen be represented by mp. This is the mass of the Payen. That should be the case. And for the sake of simplicity, let us use the units here, that h cross is equal to c is equal to 1. And then we can write down the de Broglie matter wave equation. We can write down this equation. And what's that? We can write down this the matter wave equation. The matter wave equation. What's that? So that is dou square dou t square psi of x and t minus del square psi of x and t is equal to minus m pi square psi of x and t. Where this we can write down this del square, it's a Laplacian operator, and what we have chosen is spherically symmetric situation, and we have the value for this del square in spherically symmetric situation. And what's that? We have this del square is 1 by r square dou by dou r of r square dou psi by dou r. Okay, so then plus 1 by r square sine theta dou by dou theta of sine theta dou psi by dou theta. And then what we have is plus 1 by r square sine square theta dou 2 psi by dou phi 2. Now, since we have a spherically symmetric situation here when we are trying to deal with these nucleons inside the nucleus, so there is no contribution of angular parts in the Laplacian operator, and what is assumed here is that we have a spherically symmetric solution for have to have a spherically symmetric solution for this equation, which would describe the Meson field outside a nucleon located at some origin. So this is going to be an important point, that the nucleon, the dimensions of this nucleon are extremely small, and we may consider it to be a point particle. So in doing so, what we will have for del square here, and choosing for psi, choosing this spherically symmetric potential, we can write down for this del square as 1 by r square dou by dou r of r square dou of v by dou of r. So we can use this in this equation. Suppose this is 2. So we can use it in this equation, and at the same time, what we have a situation where we have a static situation. Then immediately the time dependence of the wave function is also equal to 0. So what will happen to this equation, this matter wave equation? It will boil down. To an equation like what we will have there is minus del square v of r equals minus m pi square of v of r. This should be the case. So, but for del square, what we have for this spherically symmetric situation, we have 1 by r square dou by dou r of r square dou V by dou R is equal to m pi square V of R. That's the case. Okay, so what is it? We have a differential equation, and it's an ordinary linear differential equation of order 2. So we have this differential equation, and we can have two linearly independent solutions for this differential equation. So if I have to talk about the solution, if I write down 1 by r e to the power of minus r m pi, and we'll have 1 by r e to the power of plus r m pi. Now, the general solution the general solution of this differential equation will be the linear combination of these two independent solutions. But the problem that we are talking about here, it's to be noted here that the second solution that we have here, it corresponds to potential which increases beyond limit with increase in R. Thus, this second solution is unacceptable physically. Hence, the solution that we should write for it is V of R is, let me use C dash, C dash of then exp of minus R m pi by R. So this is our Yukawa potential, and this C dash is a constant. And thus we conclude that this potential energy of two stationary nucleons that are separated by distance r, and if we have to write down that in terms of potential energy, we can use another constant here, and we can write down the solution. So this equation that we have here is a representative of the fact that the potential that we have obtained is the Yukawa potential, and we would like to have incorporation of this potential in the Meson's theory in the next video, where we will incorporate this solution to a situation where we will have some calculations and some discussions based on this nuclear force. And what more I should do here is that I would like to choose this MP as a reciprocal of some lambda, 1 lambda pi. So if I have to write down the potential energy equation, I can use C by R exp minus R by lambda pi, where this lambda pi is defined by the mass, the reciprocal of the mass. So would like to stop here. Now, let's move on from the previous video where we talked about Yukawa potential, and we have the Yukawa potential energy as given by this equation, and we have introduced lambda, and one thing has to be borne in mind, that we have chosen h cross equal to c equal to 1. So we can include these parameters at some point later, but right now what we have is this equation, and this equation defines the potential field which is operative between two nucleons inside the nucleus. And but this potential is not, one thing has to be kept in mind, that this potential is not operative outside this nucleus, and it is different from that of electrostatic field, as it is charge independent right now, and it has very short range, and an operative example can be deuteron, having dimensions of the order of 3 to 10 to the power of minus 15 meters, nearly 3 Fermi. And In analogous with electrostatic forces, this nuclear potential that we have, we call it as Meson field. So this is called as Meson field. Because of the hypothetical particles, mesons are exchanged between these nucleons. They are exchanged between these nucleons, which is responsible for the nuclear binding. Now, to demonstrate this thing, if I have to think of if I think of a proton and we have an exchange of a negative meson, that is pi negative, and what we have is neutron. And if I show it in the opposite direction, then we will have pi positive meson, and we will have proton. Now, to account for the binding force between the neutrons, neutron and neutron, the existence of neutral meson was postulated, and it was introduced. Since the nuclear force field must be attractive, it has to have attractive nature. Then the equation that we wrote down is for U equals minus C times e to the power of minus r by lambda pi by r. So this overall potential should be negative. And then only then this can account for the attractive force between the nucleons inside the nucleus. And this is because of this mesonic force field that we have the proton and the neutron, and they may be assumed to carry charge, and they may be assumed to carry charge, a mesonic charge, assuming to be F. So the way we have Q1 for Coulomb's law, if we write down, we have the product of these charges, or for potential energy, we have the product of these charges in electrostatics. In analogs to that, what we have here is F scat, and this F scat should account for this C that we have introduced here in the potential energy. So what's going to happen? So replacing this, so we'll have U equal to minus F squared by R e to the power of minus R by lambda pi. Now, moving on from here, we can compare this minus F squared by R with the potential. Now, if I choose a potential like U of R equal to minus F squared by R e to the power of minus alpha R. Okay, so where this alpha, its value is nearly from 0.3 times 0.5 whole to the power of into 10 to the power of 13 centimeter inverse. And so putting it as inverse for 1 by lambda pi. So 1 by lambda pi is taken as alpha here in this case. So what are we going to write down when we go back to the equation that we have, the equation of del square by del t square of psi of x and t minus del square of psi of x and t is equal to minus m pi square psi of x and t. So to look at this equation, what we have here is we have to introduce for this m pi square, and we have to introduce here for for this m pi square. So what can we do here is we can write down this equation as dou 2 by dou x2 minus alpha square psi equals 1 by c square dou 2 psi by dou t2 function psi. So what we have here is what we have is that the differential equation that's dependent on time, and alpha is defined. Now the quantum of nuclear force field can be derived by considering psi to be of the form as psi is equal to a sine of kx minus omega t as the solution to the differential equation here. Let's consider this as equation 1. So to move on from here, what I would like to do is I want to get the double derivative of this wave function. So I will have d psi by dx. So k will be out, a cos kx minus omega t will be the first thing, and psi will be with it. Let us differentiate it again with respect to x. It's going to give me k square, and that to minus of a sine kx minus omega t. All right. So here is no psi, so this thing is psi. So d2 psi by dx2 is minus k square psi. So what I have is I would like to introduce this d2 psi by dx2 that I have in this equation. I have missed it here. Okay, for this I have this thing, and I would like to substitute this 2 in 1. So substituting second in 1, what am I going to get is minus k square of psi minus alpha square of psi is it is 1 by c square of dou 2 psi by dou t2. So this would be the result for the time being. So call it 3. Now what would I like to do is I would like to differentiate it with respect to time 2 times. The same equation that I have for psi. So differentiate what I have, psi equals a sine kx minus omega t. So d psi by dt will be minus omega a cos kx minus omega t. This omega is the internal derivative of this omega t. Then d2 psi by dt2 is minus omega square a sine kx minus omega t. So it will become so this will be the case, and what will I get is d2 psi by dt2 will be minus omega square of psi. So we can use this this equation also in equation 4. So this is my equation 4. So I would like to use for this. Okay, so what I'll get, substituting 4 in 3. So to say what am I going to get is minus k square psi minus alpha square psi is equal to minus omega square by c square and then psi. This will be the part of this equation, and we can boil down this equation, and we can, for k, what k is, that is 2 pi by lambda. Okay, and we can write for omega is equal to 2 pi nu, and we can have minus, that's k square is 4 pi square by lambda square psi minus alpha square psi is equal to 1 by c square times minus 4 pi square nu square of psi. Okay, or we can boil down this as nu square by c square is equal to 1 by lambda square plus alpha square by 4 pi square. So finally what we will have is we will have h square nu square by c square is equal to h square by lambda square. I'm multiplying this equation by h square. It's not cross, sorry, it is only h. So plus alpha square, then h square by 2 pi whole square. So what we have done is we have multiplied this equation by h square. Now what we have here is this expression that I have. It gives the frequency of the de Broglie waves that are associated with these mesons. De Broglie waves associated with mesons that we are talking about. And the rest mass of this meson is m0, which has to be attributed to the meson when it is considered as a particle. So we have to attribute it as a mass of m0 instead of choosing it as a wave packet. And we can have this we can as a particle we can write down the energy of this meson as m naught square c to the power of 4 plus p square c square. And what we know is that E is equal to h nu and P is equal to h by lambda. So from these equations, if we see here, what is this? This h squared by lambda squared. It is p squared, simply. It is p squared. So we can go with this equation, and we can think of E squared equals c squared. I'll get out from this equation. What will be inside will be m naught squared. Then I will have c square plus what else I have is p square and c square. Now if we look onto this equation, that every term in this equation, because this equation is dimensionally correct, so every parameter in this equation is a representative of the same physical quantity. So this thing is this thing is p squared. Okay, so this thing is also p squared. So what can I do here is that I can introduce that thing here. So what will I have is where is that? I will have is okay, here I have got it out. So what is inside? I have p squared inside. Okay, so E squared. Now looking at this equation a little bit closely, what does it mean is that this term and this term is the representative of the same thing, at least dimensionally. So what we can say is that this m naught square c to the power of 4 is equal to this what is that, p square. And what is p square? That's alpha square h square by 2 pi whole square. So for p square that I have here, I want to make sure that this m square c to the raised power 4 is equal to what is it equal to? It is equal to h alpha by 2 pi whole square times c square. So this is for p square that I can choose from this equation, okay? And because this equation is an equation of momentum square. And what else I can talk about here is that I can calculate this rest mass of this meson, and this equation will boil down to h alpha by 2 pi c. And now what we are going to do is we would like to have the values for these constants in this equation, and we can calculate this rest mass of this meson. So what will be that is, for what we have is m0 is h alpha by 2 pi c. We know h, that is 6.62 into 10 to the power of minus 27. We can write it in terms of ergs second, and C we can take as 3 into 10 to the power of 10 centimeter per second, and alpha is measured as 5 into 10 to the power of 12 centimeter inverse, because it is the reciprocal of lambda. So using these values, we obtain m naught. That will be what? That will be 6.62 times 10 to the power of minus 27 times 5 times 10 to the power of 12 centimeter inverse, and divide by 6.28 times 3 times 10 to the power of 10. All right, so this is my 2 pi. So this value comes out to be 1.76 times 10 to the power of minus 25 grams. And we can convert it into kilograms. This is 1.76 times 10 to the power of minus 28 kilograms. So this is the mass of the pion that comes out from this calculation. Now, if we compare this mass with the mass of the electron, so what is mass of the electron? It is 9.1 into 10 to the power of minus 31 kilograms. And what is the mass of the pion? That is 1.7. It's 6 times 10 to the power of minus 28 kilogram. And this is clear from this equation that this Yukawa particle, which is a meson, it must therefore have mass of about nearly 190 times mass of electron. And if we go back to the Yukawa potential, where is that? That was U of R equals, it equals C e to the power of minus R by lambda pi divided by R. So this was our Yukawa potential. And due to this exponential factor that we have, the potential U of R decreases very fast. It decreases rapidly as this R increases. So we can say here that it's a short-range force. So it is a short-range force. It is a short-range force. And very nearly, one may say that the range of this potential that we have between the two nucleons, where it has its own power, the nuclear energy, that this range is of the order of the lambda pi that we have introduced. And beyond this distance, the potential eventually completely becomes negligible. There's no potential at all. Now, it is now known that the mass of the pion, the mass of this pion is of the order of 140 mega electron volts. And the quantity, this lambda pi that we have here, this lambda pi is equal to introducing H cross. This is H cross by m of pi that we have chosen, and C. This lambda pi is of the order of 1.4 times 10 to the power of minus 13 centimeters. And it's nearly 1.4 times 10 to the power of minus 15 meters. So this is the range of the nuclear force, this lambda pi that we introduced in our original equations, where we chose H cross equal to 1 and C equal to 1 for the sake of mathematical simplicity. This is the range of the nuclear force field, because it is the range of the inner nucleonic force that we are talking. It was also known to the man Yukawa, from the variety of experiments that he performed, that the range of this force field is of the order of 10 to the power of minus 13 centimeters. Thus Yukawa's theory agrees exceedingly well with what was experimentally observed, what was experimentally demonstrated, what was experimentally calculated. So it's worthwhile to note that we have found Yukawa potential by assuming it to satisfy a linear wave equation that we started with. In fact, the quantum force field they obey these nonlinear equations, and the linearized theory that we have used is only an approximation valid only outside this span of wavelength greater than 10 to the power of minus 13 centimeters. So numerically, Yukawa's potential comes out to be, it nearly comes out to be minus 10.46 mega electron volts times e to the power of minus r by lambda pi, divided by r by lambda pi, and this value, this lambda pi, it boils down to 1.4 Fermi that we have here. Okay, so to demonstrate this thing in some in the graphical form, what I would like to do is I would like to have a plot of the Yukawa potential and the rough estimate of that plot. So this potential is something like this. Okay. It should go. It should almost touch it. So this is one. This is 2 Fermi, and this is minus 100, and this is 100, and this is 200. This is the potential U of R, and this is in mega electron volts. And what we can see here is the potential of the nuclear force, which is a very strong force. Field for two nucleons of anti-parallel spin. They don't, their spins are anti-parallel, and they have zero orbital angular momentum. They don't have any orbital. They are supposed to be at rest. Now, trying to have some pictorial view for this problem. I'll try to go for diagrammatic representation of this pi